Welcome back, Physics 30. This is the second book in Unit 3, Work and Power Part 2. And in this, we'll be looking at positive and negative work, distinguishing between those two, determining the component of an applied force that acts in the same direction as displacement, and calculating work graphically from an applied force versus displacement graph. So first of all, what must you be certain to do in calculating work done on an object when it is pulled at an angle from the direction of motion? And that is to find the force component that acts in the same direction, parallel to D. Yeah, so the better word there is parallel, because we could also have the force operating in opposite direction, causing it to slow down. But in this case, this picture, we're pulling it up at an angle, this wagon, so we need to figure out what is the horizontal force that works alongside or parallel to the displacement. So of course, just like before we've done, in this particular case, it's the adjacent side over hypotenuse, so of course we're looking at the cosine. So cos of theta equals fx over my f, my applied force. Solving for fx, I get f cos theta. So what you could do is use this part in the equation. Work is equal to, in this case, the applied force that I'm looking for is the actual Fx force. That's the force that operates with delta D, parallel to delta D. So Fx can be found as the actual applied force in the question times the cos of D times delta D. So you could actually use this equation. And in fact, you can use this equation all the time, because if we were pulling it along Fx, that theta would be 0, and the cos of 0 is 1, so it wouldn't change. So we could use this equation all the time if we wanted to. And this brings in the idea, well, how come when you have a force that's parallel to the direction of motion, it's 0? Because, of course, from math, you know that the cos of 90 degrees, which is what that angle would be, is 0. So none of that component would be causing the movement to happen, so there's no work being done with that particular force being involved. Excuse me, so that's why the cos of 90, or perpendicular force and displacement, causes no work. Okay, some questions. A wagon is pulled 20 meters along a level surface by its handle. If the handle makes an angle of 15 degrees with the road, and the force exerted is 60, how much work is done? So we have this scenario looking like this. We're pulling the wagon to the right, but we're pulling it up at an angle of 15 degrees. It's 60 newtons. We know it's moving to the right, so we're concerned about figuring out Fx. And of course, from earlier, cos of theta is Fx over F. Solving for Fx, F times the cos of theta. So we could use that in the equation there. As mentioned, we can use it all the time. The equation, instead of work equals Fd, we could make it work equals F cos theta D, and then we'll be able to handle all angles involved. So we get 1,159.110. Looking at all my numbers here, they're all 3 sig figs, so 1, 2, 3, the 9 bumps us up to a 6, so 1160 for joules. A rope is used to pull a metal box 15 meters across the floor. The rope is held at an angle of 46 with the floor, and the force is 628. How much work is done? Maybe pause the video right now and run through that and see what you end up with. It's very similar to this previous one. Okay, if you had a chance to do it, of course, this is this scenario here, pulling it up at an angle of 46 degrees, 628 newtons. So W equals 4F cos theta D, and we get 6,540 joules when we round off the correct number of sig figs. Explain why holding a box up off the ground involves no work. Getting the box off the ground involves work, but actually holding it there for any length of time is no work, because we're not moving it. We have a force holding it up, but it's not moving, so no work. And as I mentioned here before, I kind of asked these questions already previously. Holding a box up, walking forward, the force is up, you're walking forward, so they're perpendicular, and of course that cos of 90 is 0. But yes, lifting up an object off the ground does involve work, because you have force and displacement are occurring in the same direction. Next, a 50 kg dancer runs up with constant velocity up a flight of stairs. If the vertical distance of the stairs is 56, what is the work done against gravity? Now, with this scenario, whether you're walking up a flight of stairs or climbing up a vertical ladder the same distance, it's the same amount of work. Of course, doing some of this work is easier going this route as opposed to this route, but it's the same work. So moving up the stairs, what you're doing, the force you have to exert is against your own body weight. So the applied force is equal to Fg, which of course is mass times gravitational acceleration. So you're working against your own body weight. So we could say the force applied is actually Fg when we're going up vertically. That is equal to mg. So 50 kgs times 9.8 times the vertical distance of 5.6, 2,740 joules. So that's one thing to consider when we're talking about running upstairs or going up vertically. Shortly you'll be doing a power lab that involves this, and you will calculate your work done, and you'll be using basically your body weight as the force that you must overcome. Another example here, a 71 kilogram window washer stands on a 179 kilogram platform suspended on the side of a building. If the motor raises the platform up 58 meters up the side of the building, how much work is done by the motor? So we have a total mass here, U and the platform. Work is equal to mgd, so the 250 is the mass. Acceleration of gravity, that part will give you the weight. And moving up 58 meters, so 142,000 joules. One last question here. A forklift raises a box 1.2 meters, doing 7,000 joules of work. What is the mass of the box? So here we go again, folks. We have W equals force times displacement. Since we're moving something up vertically, it's work equals Fg times displacement, or we could simply say mg delta d. So solving for m divided by gd, and we get this, and works out to be 600 kgs, or 6.0 times 10 to the 2 to indicate that we have 2 sig figs. Now, positive work versus negative work. As I mentioned before, work is a scalar quantity. It's not direction dependent, but yet we can have positive work and negative work. Positive work is when the force and displacements are in the same direction, so the object gains energy. So when you're lifting up a barbell to military press it over your head, that is positive work. Negative work is when F and D are opposite directions. So something's moving this direction, but you're having a force in the opposite direction. So of course that object is going to lose energy. So lowering the barbell back down. Your force is upwards, but the barbell is moving downwards. So that is negative work. So positive work, the object is gaining energy. Negative work, object is losing energy. So if we take a look here, involving pushing a wagon, if you're pushing the wagon in the same, if the force is in the same direction as motion of the wagon, then that's positive work. Or if the wagon is coming towards you and you're pushing in the opposite direction to slow it down, losing energy, that's negative work. Okay, the last thing we have here with work is, since work is equal to force times displacement, very similar to what we did in Unit 1 with displacement on velocity time graphs, we can use a graph to figure this out. And of course we'll have just simple, we don't apply calculus here, so we'll use simple shapes, whether rectangular or triangle. So if you have a force displacement graph, work is equal to force times displacement, which is equivalent to length times width, or in a triangle, to figure out the area of that, it's half the base times the height. So if we have a scenario like this, you have a graph here involving pushing an object along 20 meters, increasing force, constant force, increasing force. You can see how I divided that up into rectangles and triangles. Here you have a triangle, half the base, half of 8 times 5. Then I took this whole section, this whole rectangular, from 8 to 20, is 12 times 5. So you can see that part there. And then this little section from 16 to 20, that's actually a difference of 4, 3, and it's a triangle, so a half. So a half times 4 times 3, so 86 joules there. Very similar to what we did earlier with velocity time graphs when figuring out displacement. And we have this one here. You may want to just stop the video, see if you can work it out. When we have this constant force of 12 newtons along 7 meters, then the final 2 meters we decrease the force until 0. So if you had a chance to do this, length times width, or length times width, 7 times 12, and then over here from 7 to 9, be careful, this isn't 9 here for the base of the triangle, it's only from 7 to 9, which is 2. Half of 2 times 12, 96 joules. Okay, so that's it. So we had 3 basic things with there. The component of a force, positive and negative work, and of course the graphical way of determining work. So kind of reinforcing that now, positive work, F and D are in the same direction. The object gains energy, whereas negative work, F and D are in opposite direction. The object loses energy. Okay, I think that's it for the Part 2 booklet. So it was a somewhat bigger booklet than the previous one, but I don't think it was too difficult. Okay, we'll see you again for booklet 3 soon.